So now that we've seen sort of a big picture or overview of ordinary differential equations, and we talked about how to determine whether a set of functions was linearly dependent versus linearly independent. Now let's talk about some general aspects of the solutions to the linear homogeneous ODE. And this is section 3.3 of Greenberg's text. And the title is the homogeneous ODE, the general solution. So we're going to talk about properties, very important properties, of the general solution. So our general n-order homogeneous linear ODE can be written as the nth derivative of y plus some coefficient, which is a function of x. So this is p sub 1 times y, the n minus 1 derivative of y, all the way out to the nth coefficient, which is a function only of x, times y is equal to 0. So again, we put all the functions of y and its derivatives on the left-hand side. Anything that's completely independent of y we put on the right-hand side. And so this is homogeneous because there's no function that's completely independent of y. And you can see that we have a linear equation because there are only coefficients multiplied by y and its derivatives, not powers of y or its derivatives or other nonlinear functions of y or its derivatives. So again, this is the general linear homogeneous ODE of order n. And I'm going to refer to this equation again. It's equation 4 on page 83 of Greenberg's text. So I'm going to refer in this video to equation 4 multiple times. Now, the general solution to this it encompasses all possible solutions. Okay, so the general solution describes all possible solutions. Remember, there's an infinite number of solutions because we have integration constants that can have an infinite number of values. And the particular solution is one among the family that meets the specific initial condition or boundary conditions. Right, so the particular solution will have a particular value for the integration constants, and those values will meet the initial condition or the boundary conditions or both. So this is some sort of general aspects to remember about the general ODE and its solutions. Now let's talk about Theorem 3.3.3. Sorry, 3.3.1, and it's with regard to the existence and uniqueness for the initial value problem. And this theorem states that if the coefficients that is P1 of x, P2 of x, etc., are continuous on I, that is the interval in which we evaluate the solution, the interval being the range of x at which we evaluate the solution. And given the initial conditions, y at a is equal to b1, y prime at a is equal to b2, y prime prime at a is equal to b3, all the way up to y, the nth derivative of y. So if we have, for an n order initial value, ODE, that's an initial value problem, if we have n initial conditions defined on the n derivatives, then the equation has a particular solution, and this solution is unique. And by unique, that means that there is only one solution, one combination of values of the relevant integration constants that satisfies this one initial condition. And so this theorem, again, is the statement about the uniqueness and existence of a solution for an initial value problem. A second theorem, and we'll talk about this a bit more, is Theorem 3.3.2, having to do with the superposition of solutions. Superposition, S-U-P-E-R-P-O-S-I-T-I-O-N. And this theorem states that if y1 of x, y2, the numbers refer to different functions of x. So if there are n distinct functions that are solutions to equation 4, that's our general linear n-order homogeneous ODE, then so is the sum C1 y1 of x plus C2 y2 of x all the way up to Cn yn of x. Right? So if there are n different functions that satisfy the general equation, whatever it is, whatever the coefficients are for a given problem, then the sum of all those functions multiplied by arbitrary constants then the sum of those functions when multiplied by these arbitrary constants is also a solution. I should say, right. This is also a solution. Okay, so those are two theorems. Let's go into some properties of the linear ODE, uh, and we'll use a slightly different notation. So we could rewrite equation 4 as capital L square bracket y is equal to 0. So this is um, a short way of writing equation 4. Again, equation 4 is our general equation for a linear homogeneous ODE of n order. And so the letter L denotes the operation the nth derivative with respect to x plus p1 of x times the n minus 1 derivative with respect to x plus all the way out to pn times, pn minus 1 times the first derivative with respect to x plus pn plus pn, and all of these are functions of x. And that's right. So that's what the capital L function does. It's an operation like this, and we would read L bracket y as the L operation acting on function y. Okay, so for example, right, so that is L acting on function y, again, is the nth derivative of y plus p1 of x times the n minus 1 derivative of y all the way out to p n minus 1 times the first derivative of y plus pn is also a function of x times the first derivative of y plus pn of x times y. And right, and so when we can say that this function is equal to 0 to describe the general equation. Likewise, we could operate L on some other function, u, and we would get u raised to the nth power plus p1 times u raised to the n minus 1 power all the way out to pn of x times u. So this is just a short way of writing the left-hand side of this general equation, and we can express the general equation by equating that equal to 0. So L is a linear operator, and a linear operator has the property, for example, that when we operate L on a function, say alpha, which is a constant, times u of x, plus another constant, beta, times another function, v of x, when we perform that operation on the sum of these two functions, that's also equal to alpha times L operated on u plus beta times L operated on v of x. So this is a property of a linear operator. When you operate on the sum of the two functions, that's equal to alpha. It's the sum of the operation on the two functions separately. So likewise, L operated on C times y1 plus C2 y2 is equal to C1 L operated on y1 individually plus C2 times L operated on y2 individually. And this is true also for greater than two functions. So we could operate on three functions and get the sum of three separate operations and so forth. So let's look at an example of a superposition of solutions. So the equation we're asked to solve, and Greenberg includes this example, is y prime is equal to 9y is equal to 0. Oh, sorry, y double prime minus 9y is equal to 0. And it turns out there are two solutions. And two solutions can be described as y1 is equal to e to the 3x, and y2 is equal to e to the minus 3x. And we can verify that y1 is a solution because if we take the first derivative of y1, we get 3 e to the 3x, and the second derivative of y1 is equal to 9 e to the 3x. And therefore, when we add the second derivative of y1, or we subtract y1 from its second derivative, that is y1 double prime minus 9y1, we get 9 e to the 3x minus 9 e to the 3x, and indeed that's equal to 0. Good. Likewise, y2 double prime minus 9y2 is equal to 9e to the minus 3x minus 9e to the minus 3x, and that's equal to 0. So we've verified that each of these solutions solves this equation. And likewise, you can show that the combined function y is equal to, for example, c1 e to the 3x plus c2 e to the minus 3x also is a solution. And I encourage you to go ahead and prove to yourself that this is true. You can work that out for yourself on your notes. So now I'd like to present probably the most important theorem that's relevant to what you'll be doing in solving these equations. And if you remember anything from this video, you should remember this theorem. And this is Theorem 3.3.3 on the general solution. For the n-order homogeneous linear ODE. And this solution states that the general equation that is equation 4, which we also wrote as L, the general n-order linear operator on y is equal to 0, that general equation has exactly, no more and no less, n linearly independent solutions. And those solutions are y1 of x, y2 of x, all the way up to yn of x. They're linearly independent, so no two can be described as a linear combination of each other. And the general solution, which again encompasses every single possible solution, the general solution is y is equal to c1 y1 of x plus c2 y2 of x. It's the sum of all of these linearly independent solutions. Where the C1, C2, up to Cn are arbitrary constants. Okay, so again, this is a very important theorem. So when you solve an n-order homogeneous ODE, you'll have to you'll need to find the n linearly independent solutions to have the complete general solution. So let's go back to our example here, the one that we looked at when we showed the example of superposition of solutions. So again, this is our differential equations, and we'll go through later how to solve this, but it turns out that the solutions include, and you can check this yourself, you can verify that each of the following are solutions. That's e to the 3x, e to the minus 3x, 5 e to the 3x, 2 e to the minus 3x, hyperbolic sine 3x, and hyperbolic cosine of 3x. So there's lots of different forms of solutions, but among all those possible solutions, there are only two linearly independent solutions. And so your general solution should be given in terms of exactly two linearly independent solutions. So the two solutions we first looked at were e to the 3x and e to the minus 3x. Another valid answer would be c e to the 3x plus c2 times 2 e to the 3x plus e to the minus 3x. Or another valid answer would be c1 e to the 3x plus c2 sinh 3x. And you'll recall that sinh 3x is equal to e to the 3x minus e to the minus 3x over 2. So each are equivalent and valid ways of expressing the general solution. And you would choose the form that you're, well, most comfortable with, but especially you would choose the form that makes meeting the initial condition the easiest. So depending on the initial condition, it may be easier to express the solution in terms of a hyperbolic sign or as an exponential function. And Greenberg goes through some more details of why that might be. Let's go over one more example here. So if we have y triple prime plus y prime is equal to 0, the valid solutions, there'll be 3 linearly independent solutions, and those include cosine x, sine x, and a constant, right? So we can see that if we're working with cosine x, y prime is equal to minus sine of x, y double prime is equal to minus cosine x, and y triple prime is equal to sine x, so that when we add y triple prime to y prime, we get sine x minus sine x, and that's equal to 0. We could do something similar for using the solution sine x, and you should be able to convince yourself you'll get the same solution. And likewise, any derivative of a constant will equal 0. So this is also a solution. So the general solution should be written as y is equal to c1 cosine x plus c2 sine x plus c3, or just our constant. And again, just to use the notation we used before, if the linear operator is given, if our equation is described as this linear operator on y, and that's equal to y triple prime plus y prime, we just showed that L operated on cosine x gives 0. You could show yourself that if you operate L on sine x, you'll get 0. And of course, when we take derivatives of constants, then that gives 0. And again, verifying the principle of superposition, if these are individually 0, the linear nature of the operator will allow us to state that the sum of a linear combinations of those functions is also a solution. So I think I'll conclude here. This was a couple of video series on some general aspects of linear homogeneous ODEs of second and higher order.